I put up these two pictures as a start because it's the last of anything human you're going to see from my talk. But these are the precursors. Planck in 1900 invents the quantum. Einstein in 1905 says, "Oh look, it isn't just that things get absorbed and emitted in these quanta. Light actually comes in quanta. It's granular." That was a very shocking idea, not quickly accepted, because we knew that light was a wave. A little while later, Niels Bohr, in a kind of almost musical, mystical derivation, shows how to find the frequencies of light that are emitted from a hydrogen atom. And what he's really just showing you is that a hydrogen atom can only have certain energies, cannot have just any energy. And that's kind of the big message of what I wanted to talk about today, is how you get there. That's the last time we talked, I was showing you how you get into wave particle duality, how things seem under some circumstances to be waves, but the exact same things under other circumstances turn out to behave like particles. And quantum mechanics is necessary to resolve that contradiction almost. How can you have something which is both a particle, which is localized, and a wave which is spread out in space? How do you do that? How do you do both of those things at once for the same object, same substance? And we'll talk a little bit more about that, I think, today. Anyway, Bohr was kind of the first one to show that somehow or other, in the problems that these men were facing, you had this discreteness of energy states, that an object could not just have any energy. It could only have certain well-defined energies with nothing in between those well-defined values. Very, very strange. And then the next step was Heisenberg trying to explain the emissions that come from atoms, really kind of dealing with something that Bohr had already dealt with. And Heisenberg, I don't know, always when you make a big advance in science and theory, there's something going on deep in somebody's head, and it's never clear how they come to where they finally end up. And Heisenberg famously suffered badly from allergies, and it was coming spring, and so he went up to Helgoland, to an island, through the island, where the sea breezes would keep the pollen from him, and he could breathe easily. And while he was there, he saw a kind of relationship, a mathematical relationship, that seemed to apply to the emissions, spectral emissions of atoms. And he wrote this down, and he took it back to his mentor, Max Born. And Max Born said, basically, he said, "You have just discovered, he said, your mathematics is matrix mathematics. You are just multiplying matrices together." Most physicists in those days had no knowledge of matrices, and not at all surprising that Heisenberg wouldn't. Born happened to be rather singular among the physicists. He recognized what Heisenberg's mathematics were. So Heisenberg had, with those mathematics, created quantum theory as we know it today. Born, in effect, explained to Heisenberg what he had done, and was kind of was definitely put out when, in 1932, Heisenberg got the Nobel Prize, and Born didn't get squat until 1954. There was a sort of long period of time, and then Heisenberg had published his stuff. Dirac, very young man at the time, sort of looked at what Heisenberg done and said, "Oh, I see the whole thing." And he wrote almost a definitive quantum mechanics book. It's still a wonderfully basic book, and sort of laid out a complete theory of quantum theory. So sort of took what Heisenberg had done, and then Schroedinger did a completely different thing. He invented something which we call the wave equation. So in a way, if you want to keep the wave-particle duality in mind, Heisenberg and Dirac were formulating a mathematics which had a kind of particle field to it, and Schroedinger formulated a mathematics that had a kind of wave field to it. And for a little while, people thought, well, this is weird. They're just two completely different things, until when the real mathematicians got into this, they were able to show you that Schrodinger's wave formulation and Heisenberg's matrix formulation were equivalent. You were seeing, you had the same fundamental mathematics, and you were at least consistent in your mathematics. So that's kind of the whole history of quantum mechanics. 100th anniversary of Heisenberg's paper will be in 2025. It's just a few years from now. One of my hobby horses that I ride is that, don't you think after 100 years we should have quantum mechanics in the introductory course somewhere? Introductory physics, why do you have to wait 2 years before you get to quantum mechanics? Anyway, that's just a big historical introduction. I want to talk again, sort of the next stage of why we need quantum mechanics. And last time it was wave-particle duality. This time I'm going to go down to the discreteness of system energies. That's kind of the major point today, that things have distinct energies, and that corresponding to that is discreteness of structures. That we go through all this stuff about CRISPR, and people are talking about DNA, and it's they're talking about these things like they were Legos, like that things go together and this fits into that and that locks into this, and nothing bends, nothing has much flexibility to it. And if it were not so, we would not have these wonderful biophysical mechanisms that we so carefully describe. And if it were not, so that is the way the world is. The world produces these sort of ball and stick atoms, molecules. But the theory has to describe that if it's going to be a good theory. And so the theory that describes that is quantum mechanics, and it is the discreteness of structures that finally gets us there. But I wanted to do some other things before we get there. Like I want to just go back over, I want to show you some formulas because I like them, and you'll see they kind of have some, they'll show up in nice ways. And also just remind you about double slit interference. It says here I'm going to remind you about Zhou, Wang, and Mandel. I'm not. And then talk about what nature won't let us know. And therein is the so-called Heisenberg's uncertainty principle, which is very badly named, I think. Anyway, I want to talk about it and what its kind of physical consequences are, because they're quite remarkable. And it underlies the way the theory prevents you from sort of having a contradiction between waveness and particleness. The uncertainty principle is a way of just saying nature is constructed so that you can never at the same time produce wave properties and particle properties. You can produce one or you can produce the other, but the very act of producing the one prevents you from producing the other. It's very nicely constructed. So that's the story. Then just so you have something to look forward to, I'm going to end with Schrodinger's equation as folk art, but I'll tell you the story about that when we get there. So here's some basics. I'm going to talk about momentum quite a lot. Those of you who remember anything from introductory physics know that momentum is mass times velocity. Newton called it quantity of motion, which was actually a very nice idea because he was just trying to say how much motion resides in an object. And the motion comes partly from its velocity, but a small object with a high velocity can have the same amount of motion in it as a big object with a small velocity. And I'm showing you that it's written as P. That's the main reason for showing you the equation, is because in physics, and I'm going to use P often to refer to momentum. So that's that. And then there's kinetic energy, which again, you might remember is a half mv squared, the energy associated with the motion of an object. But again, since I'm talking about momentum, you should understand, and it's just a piece of simple algebra, that kinetic energy is p squared divided by twice the mass of the object. And I mean, it's like that, that's just synonymous with the kinetic energy. But again, I'll come back because I'll be referring to the kinetic energy somewhere. And the thing that quantum mechanics does, I mean, this is classical Newtonian physics, is that this constant H connects the wave properties and the particle properties. It connects wavelength to momentum. This one I think I referred to last time as de Broglie wavelength. But if you have an object with, if you have an electron with a momentum p, you divide that into h, and it gives you a wavelength. I mean, it gives you a length. If you do the, the units of h and the units of p are such that when you divide them, you get a length. And that's the wavelength that an electron will exhibit when it undergoes interference in a two-slit. That's the wavelength that a neutron will exhibit when it undergoes interference. So here's quantum mechanics connecting wave to particle phenomena. I mean, we think of momentum as a particle quantity and wavelength as a wave quantity. And then we have also that this is what Einstein and Planck first and then Einstein definitively said, look, there's a connection between frequency, another wave property, and the energy of the object. And this is the photon doing its stuff here. And it's all tied together by this constant down here, which we have, well, there's a whole nother story there. This used to be something you measure. If you want something to think about in the middle of the night, you say, it is no longer measured, it is now defined. And its definition is what determines the mass, the value of the kilogram. That's a whole nother story sometime. And I shouldn't have brought it up now, it was unkind of me. All right, this business of E and HF, just so you know, two other things. E can be equal to, it's often written as H nu, because physicists use nu as a symbol for frequency, the Greek nu. So I do that. I'm a professional, I have to do that. But when I'm teaching courses, I use F because it seems to me kind of handy to have F be the frequency. This one, H bar omega, is this H bar, the H with a line through it. That's an animal that's around a lot. And I'll show you some of it again. H bar is H divided by 2 pi. And omega, well, omega is 2 pi times the frequency. So that's just physics notation stuff. So H bar omega and H nu are the same thing, but H bar is around a lot. Sometimes you'll see physicists writing 2 pi H bar as though they're, which is of course H, but you won't know it. Well, I don't need to badmouth physicists. Here we go, back to reprise, what we were talking about last time. Interference means light as a wave. And what's, so if you have a wavelength and you have a spacing between two slits, the radiation coming through there will end up broken into, in this case, a pattern, which is, you can faintly red here, blob, faintly red blob here, quite a bright blob here, not so bright here, and fainter here. That is the interference, that is the double slit interference pattern. The smaller breakup has to do with the width of the slit. Narrow width causes there to be single slit diffraction, which shows up right on top of this. But the double slit is here in the big pattern. And what I told you before, which is, I think, quite fascinating, is you say to yourself, I did show you an experiment in which this is being produced one photon at a time, or one electron at a time. You just sit here and you watch with your detector, and and it goes click, or something lights up, and then it uh, it um, and after a while the pattern builds up. Excuse me a minute. I'm muted. Anyway, had to deal with a local family crisis, but what did I do? Okay, here we go. So anyway, someone says, well, look, if it's coming one at a time, why can't I put a detector out here and maybe have the photon coming through the slit tell me which slit it came through? And people devised all kinds of mental experiments where you're going to figure out a way to know through which slit the particle came. Well, it turns out if you do that, the interference pattern goes away. There is no known way to do this. And in fact, we would now say it's a law of nature. You cannot do that. You cannot have, and I showed you the the Wang Zhou Mandel experiment, which is an extremely intricate and very lovely experiment, which just shows us again how there is no way to both exhibit the kind of particleness of what's coming through there and the interference pattern at the same time. You either have one or you have the other. And anything you do to try and make it be the one prevents you from having it be the other. So that was kind of the story where I was coming last time. And, it makes people uncomfortable that it should be so. I can remember feeling uncomfortable, but after a while you get old, you just get used to it, and that's what I think a lot of understanding is. Mike, you have to unmute yourself.
Yeah, I did. Yeah, you could link those single photons coming through and the pattern in terms of probability, which also links in a way to what goes on in quantum mechanics.
Yes, the trouble with I'm going to get to some probability because you can't handle quantum mechanics for very long without it. But probability in quantum mechanics is a little different than probability in in the casino.
Yeah. Well, yeah, but what I'm saying is that when you showed in the previous lecture, discrete things coming down.
Yeah.
This final pattern that you have in terms of the intensity really is the probability, is a probability function for whether that photon would come down in any particular spot.
Okay, I certainly don't disagree with that, but I still. What's interesting is you can actually make arrangements in which you get some partial information. That in effect, sometimes you can tell through which slit the photon went, and sometimes you can't. And when you set up an experiment like that, you get a mixture. You get a mixture of an interference pattern, only now you start to see things where the dark spots were here in the pattern. And you can kind of go, the more you know about which slit the particle came through, the less interference pattern you get, and so on. Anyhow, that is takes me to something. Let's see if I can do this now. I want to get out of, I don't want to leave the meeting. Oh yeah, here's what I want to do. So I want to just talk a little bit about waves on a string, and I want to talk a little bit about superposition again. And I talked about superposition last time, and I showed you that in some physical systems, very simple physical system of say something with tied at both ends, a string tied at both ends, plucked. And then you can ask yourself, well, what wavelengths can it have? And this is obviously one wavelength. It's kind of like a jump rope or something like that. I mean, you can imagine this one wavelength going back and forth and back, going there and then up and down and so on. And this is a physical system which has sort of these very definite allowed vibrations. This is one. It's a half a wavelength fitting into a rod of length, some length, okay, L. I can have other things that fit in there. Let's see if I can do this without screwing up. Yeah, so there's one, there's another. And I can have another and now you see I have a whole, see, this is a whole wavelength fitting in. This is a half a wavelength fitting in. This is 1.5 wavelengths fitting in. And in fact, I'm going to do superpositions, and I only want to do it with things that are half wavelengths. And so I get rid of the one guy there, but I can actually build any wave shape I want on this string by adding together full wavelengths and half wavelengths. But I said, I'm going to, there should now become 3 of these. Yeah, so now there's 3 of them. And I can add them together. And so here I am, I'm adding together. I'm not adding them together with equal amounts of each. I'm adding the most is of the big one, somewhat smaller amount of the second one, and a smaller amount of the third one. That's the 3 of them added together. They make this thing, which is beginning to show a kind of lump in the middle. And you can see how that works if you look at it closely, because you see this one has positive amount here, but this one has a negative amount here. And when you add those together, you're going to get some cancellation. And as I said, I'm not combining them in equal amounts. And I can do something else fairly easily. I can add a whole bunch of them together, and let's see what happens. And there you see, I just added 30 of these together to get this very sharp, nice peak there. So this can be told to you as a classical story. This is me sort of putting a very steeply plucked string there. I've plucked the string right up in the middle to make a very sharp pulse. And you can say, oh, but that's really made up of all these other frequencies. And anybody of you who's been done, signal processing knows I'm just telling you about Fourier analysis here, Fourier series adding together. But, we take this whole picture, and in quantum mechanics, we interpret it very differently. And Mike had raised the issue of probability. This is, in a while, I'll show you how this can be thought of as the location of a particle kind of bouncing back and forth between these 2 walls. The same mathematics describes it perfectly. And only now we have to understand what the mathematics means differently. What it means really is that, and this was again Max Born's contribution. Heisenberg did not understand quite what you got there. Max Born is the one who said, and of Schroedinger also, what you have is the probability of finding a particle. If you go into this, if we now think of this as a box with a particle wandering around in the box, this state of the box is one in which everything is combined so that there's a low probability that when you measure, you'll find it here. There's a quite high probability that you'll find it here. And again, a low probability there. It is quite easy to add time dependence to this. And then this sharp peak will just move back and forth, bouncing off the walls. And you now have a moving particle. So there's, yeah, go ahead. Question.
I don't mean to interrupt, but just one simple question. I don't quite understand. When you
Incidentally, Peter, let me just say to everybody, I don't mind at all being interrupted. I like to get the questions. Go ahead.
So you said earlier that what you're showing is the sum of various curves, the area under the various curves, but you didn't sum them equally. You took some of one, less of another.
Yeah.
You know, what is the rationale for doing that? Clearly, you can make the point by doing it, and you have. But why do you take partial amounts of different frequencies to create what you're doing?
Okay, so one answer, I mean, there's a kind of two-part answer. One is because I wanted it to turn out like this. Okay, I mean, that's legit. I mean, I was trying to make a point that I can. But the other point is that when you're doing an experiment, let's say, suppose I was imagining myself doing a quantum mechanical experiment, I can control a lot of these things. I can control how much there is of each of the contributing wavelengths. And so I will design my experiment to produce the result I want. I want a particle well-defined location in a box. Then I have to use a lot of wavelengths, and I have to use them in these relative amounts. And I know that. And I can make an experiment that will duplicate that.
All right, so maybe my question is, how do you control the amount of a wavelength?
Well, in effect, you know, how do you do it with an oscilloscope? You've got an amplifier somewhere. I can see.
So I guess,
Charles, isn't the answer the 1/2j plus 1 in the denominator under the summation sign?
Oh, maybe if that's the level at which Peter's asking a question. So mathematically, that's how I do it here mathematically. But
right.
I think Peter was asking in a laboratory when I'm actually making this thing, how do I do it?
Or conversely, in nature, how do, you know, we can do lots of things in a laboratory.
All right,
but
let me save that for a little while, Peter, because I think maybe I'll get to it in a minute. Because again, it is a matter of superposition. I guess let me say a quick answer is each of these wavelengths has an energy associated with it, and
okay.
I can set that.
Okay, and does that correspond to things in nature, or we're extra natural here, if you will?
Well, I'm dealing with a system which was called a particle in a box, which is very idealized. But there are things like, let's take a hydrogen atom. There's an electron near a proton, and a hydrogen atom's about an angstrom across, about 1/10 of a nanometer in diameter. And that electron never gets any further away than, say, from the proton than about a half a nanometer. So it's back and forth. So yeah, this is telling me something about nature, and I'll come back to that and show you something in uncomfortable detail. Okay.
Thanks. I'll be patient.
All right. Good. So anyway, the point here again, and I like these questions because they help me emphasize to you that you can create a quantum state by superposing kind of components. Now, in physics, the components have a technical name. They're called eigenfunctions and eigenvalues, and you add them together. Same terminology is used for waves on a string or microwaves in a waveguide. But I don't want to go off into terminology. What I want to do is go back to my, oh, not that one. I want to go back here and go on and say again, now here's what's, I want to sort of recapitulate what we were just talking about. In order to get a well-defined location, I had to combine a lot of waves of different wavelengths back on the previous slide. Now, wavelength corresponds to momentum. It's inversely proportional to momentum. So what I was really doing was to localize the particle, I had to put together a lot of different momenta. I had to put together a lot of different wavelengths. And the more I put together, the sharper my localization could be. That's the quantum mechanics message here. And now you begin to see, oh, now I understand what happens. When I try to localize a particle enough to know where it is, I actually am constructing it out of a lot of momenta. And a lot of momenta is a lot of wavelengths. And with a lot of wavelengths, I completely wipe out my interference pattern. My interference pattern requires a very pure wavelength if it's going to happen. And so what I'm finding is that a spread in momenta is, I need a big spread in momenta to get a narrow spread of location. That's what's happening here. And I say that there's always a little tendency to kind of start talking as though the theory were the truth. What's the truth is nature is like that, that the localized object has to have associated with it a spread of momenta. And the wave-like object has to have a kind of vague localization. You know, a wave, you know, you can't exactly say to me, where is a wave? The way you can say to me, where is a particle? And that trade-off of knowing where a thing is and its wave-like behavior is the beginning of the next thing I want to say, which is, here we go, saying this again, that a sharp wavelength means a big spread in X. And a sharp wavelength means a narrow spread of momentum. Whereas a sharp X, just says this again, narrow spread of X. And a sharp X means you have to have a big spread of P. And so we're going to call the spread of X delta X. And we're going to call the spread of P delta P. And it turns out nature is constructed so that at some, we can be kind of rough about this. You can actually be quite mathematically precise, that the product of these two spreads is always greater than Planck's constant. Planck's constant sets an absolute minimum to the product of these two spreads. No matter, if you make delta X really, really sharp, then you're going to have to make delta P big. If you make delta P sharp, delta X has to be small. And I wrote it down with 3 different answers because, first of all, it is vague. I mean, it is kind of rough because it's a little different depending on what physical system you're talking about. The absolute best all-time great minimum is h bar over 2 for sort of a simple harmonic oscillator, for a mass on a spring, if you like. But people use h bar kind of roughly talking. People use h also talking roughly. But this is it. This sets a limit. And it is this limit that will prevent you from ever having an experimental contradiction of waveness and particleness. It's called Heisenberg's uncertainty principle. I think, in fact, in German, it is called Heisenberg's indeterminacy principle, which is a much better way of referring to it, because it isn't that it is so uncertain. It is a profound physical law. I put a box around it. It is so profound. Okay. Now, and I also say again, poorly named as the uncertainty principle, but it's a profound statement about the structure of nature, and it has in it predictive capability. You think something that's about indeterminacy, how does that get to have prediction? So here I am, I've written it again, delta P delta X is greater than or equal to H bar. And it implies the following, which I think is fascinating. It implies that localization imparts energy. In other words, if you're going to have something with a spread of momenta, it's going to have it's going to have kinetic energy. And here's just an example to show you what I mean. First of all, you can give this spread a very nice standard statistical definition. I mean, many of you recognize this for root mean squares and stuff like that. And so you say that the spread in momenta is going to be the average of the squares of the momentum minus the average momentum squared, square root. That's familiar to those of you who've done some statistics. But you know, if you have an electron in an atom, you know what P bar is. So this is P squared bar and this is P bar squared. You know what P bar is if it's in an atom. You want to, can you tell me? Of course, it's not hard to tell me because there's the answer, but it's zero. I mean, if you're localized, if you're an electron stuck around a proton and you can't get any further away, then on the average, your momentum is zero. You just don't go anywhere. Well, if that's true, then this is kind of nice because this tells me that P bar squared, it tells me delta P, it's P bar squared. And I do a little algebra and it tells me that P bar squared has to be greater than H bar squared over delta X squared. Well, that's pretty interesting. That's telling you that if you make delta X small, you're going to have big P bar squared. And if we divide P bar squared by 2m, that's the kinetic energy. And so that kinetic energy has to be bigger than H bar squared over 2m delta X squared. And if you're talking about an electron in a hydrogen atom, the sort of diameter of that hydrogen atom is about 1/10 of a nanometer. And if you put in the numbers, and you come out with a kinetic energy of about 4 electron volts. Well, that's just about the right sorts of energy for an atom. But that isn't quite what it's trying to tell you. It's telling you, you got this electron and it's down by the proton and it's got 4 electron volts of kinetic energy. It's got kinetic energy. It's moving around. Well, why doesn't it come out? You know, why doesn't it just move away? Well, the answer is that the proton positive charge is holding it with some force. And you can characterize the strength of the force by something we call the binding energy. Well, if the thing has got a kinetic energy of 4 electron volts and it's not coming out, then it must be being held with a kinetic with a potential energy of at least minus 4 electron volts. Otherwise, because the total energy of the system has to be negative or the electron will come out. That's how we measure these things. 0 would be just breaking through. Yeah, John.
Yeah.
If the
I got lost.
Okay, which John? I got 2 Johns.
If the energy was greater than 4, then wouldn't it be pulling it in?
If this is imagine you're in a little box and you're moving around. The box is holding you in. Something is holding you in, but you're moving around inside that box with a kinetic energy of 4 electron volts. And if you, if I'll talk about a nucleus in a minute, if the atom were smaller, then you turn out the kinetic energy would have to be greater.
What I'm asking, I guess what's confusing me, is
Yeah.
if the force applied by the positive charge of the proton was greater than the amount of energy in the electron, and wouldn't it pull the electron in?
If it did that, it would be localizing the electron. And if the electron, so a proton turns out to be a very small object. A proton is about 1,000,000 times smaller than the atom. And is that right? 10 to the 5th? Yeah, but it is about 1,000,000 times smaller than the atom. And so if delta X were 1,000,000 times smaller, this energy would go up by 1,000,000,000,000, except that the mass goes up by 1,000. And so the energy goes up. It turns out if you do it, the electron would, by virtue of being pulled in to the proton, would have acquired an energy of 10 million electron volts, something like that, 10 million times. But that's not satisfying, John. And Jonathan, what you
lost me at p bar equals 0. Doesn't everything go away? Isn't p bar squared also 0? And how can it be larger than
No.
something else?
That's the nice thing about averages, because P, the momentum, suppose you imagine something going back and forth along a line. It's going back and forth along a line around the origin, let's say. And so some of the times it's got P is positive. Some of the times P is negative. All right. And so you add those up. And the net effect is, because it's stuck and doesn't get very far away from the origin ever, but on the average is around the origin, P bar, the average of the momentum, is 0. You okay with that?
Okay.
Okay, now you say, well, what about the kinetic energy at any given moment? Well, the kinetic energy is always positive, because a negative P squared is positive. And so you're always adding up P bar squareds, and their average is not going to be 0. And that's where the mathematics lets you forget about P bar and say, oh, all right, I see that the kinetic energy is going to be related to Planck's constant and the mass of the object and the region to which it's confined. And I haven't got a really nice explanation for John, but the real point is that if the proton pulled the electron into the nucleus, he wants it to disappear. Well, it can't.
Well, no,
because
I wasn't saying into it, but closer.
well, that's what it's trying to do. And in fact, all right, let me, I'm going to go on and talk some more about the hydrogen atom. So maybe we can get some clarity there, John. I'll try.
Yeah, but
But
John,
Charles,
John is
Yes,
trying
go ahead.
to,
Go ahead, Tony.
John is trying to use
I was-
John's trying to use a classical, trying to use a
Oh,
classical.
it's not Tony. It's Mike. I'm sorry.
John is
Yeah,
trying to,
but I I don't want to. It's a kind of cop out for me to say, oh well. What I'm trying to show you is that quantum mechanics says you'll end up having to impart to that electron so much energy that it can't happen. And the other thing is that so if, I mean, the reason that the thing is bound at all, the reason that it's there is because the proton is holding it. It's like, maybe a good example is the Earth and the Moon. You know, the Earth has, the Moon has a kinetic energy. Its net momentum respective to the Earth is 0, because it just goes around and around. And yet, the Earth does not pull it in.
Charles,
Yeah, go ahead, Tony.
Isn't the other thing also another explanation that if the proton was pulling the electron with a higher force, it would just assume a lower orbit? That's all.
I've tried to avoid the word orbit, but
Okay.
yeah,
Then around,
yeah, well,
around
yeah.
the Earth,
I mean, in a
around
way,
the
what's
Earth.
in effect, if it pulled it in, it could bind it in an orbit, let's say, more close to the proton, but then delta X would be smaller, and the electron would have a higher kinetic energy. Just as if you pulled the Moon in closer to the Earth, it would the month would get a lot shorter, and the kinetic energy of the Moon would get a lot greater, but it still wouldn't run into the Earth. I mean, those are okay. But what we're seeing is that there is a limit to what a proton can do to an electron, and that is what gets you to the hydrogen atom. Let me just make that point a different way. This is originally when people first discovered the atomic nucleus, and then shortly after discovered that somehow or other its atomic number was about half of its nuclear mass, suggesting that somehow or other there were, maybe in a carbon nucleus there would be six. There were 6 lumps. Oh no, there are 12 lumps. That's the mass, 12, but 6 of them are charged. Original thought was, well, maybe all 12 are charged, and there are just 6 electrons tucked into that nucleus, neutralizing the other 6. And the answer is what I was really saying before is after quantum mechanics came and was understood a little bit, it was realized that was physically impossible. You could not have free electrons in the nucleus. The free electrons would be bound in a delta X, which is about I said it, 10 to the minus 9, 10 to the minus, yeah, it's a millionth of the delta X, and a millionth squared is 10 to the minus 12. You'd have electrons which had a trillion electron volt energy, kinetic energy.
Charlie?
No way anybody's going to keep that in a nucleus. And
Charlie?
So, yeah, Peter, Bob.
Before we get too far into this, let's not make too close an analogy between the moon's orbit and an electron in a hydrogen atom, because they don't actually orbit that way. The
Well,
Bohr atom is a fallacy.
I'll be there in a minute, Peter.
Bob,
Okay. All right. But still, the point is that you can have an object with a lot of kinetic energy that doesn't fall into the object that's attracting it.
right.
That's and you can also say, well, what about the neutron in the nucleus? And that's kind of interesting, because if you put the numbers in for a neutron in the nucleus, that'll work out all right, except that you'll find that the kinetic energy of the neutron is going to be of the order of not electron volts, but millions of electron volts. Now that's a problem, partly because the neutron is basically electrically neutral, and yet the neutrons have all this kinetic energy, and they don't come out of the nucleus. What's holding them in? And when you look at that, you have just discovered a new force. This is how physics works. You look at this thing and you say, it doesn't come out. It's not electrically charged. The protons are not holding it in by electric charge. Something is keeping it from coming out. And we call that the nuclear force, and we go on about our business. But that is basically how the nuclear force was discovered, is by this kind of reasoning. All right, binding energy implies there's a force holding a thing together. And that was what I just said. I think I want to I want to talk about this a little bit more. Let's see, do I have, yeah. Here's a mass on a spring. I thought I'd get a picture of something real for a minute. This is an air track, not bad. So you know how an air track works. It has little tiny holes all along the surface. You push air in under pressure. There's a very thin film of air comes out through these things. You put a V-shaped slider on top of the track. The air supports it. It is about as close to frictionless as you can get in an introductory physics lab. It's really good. And so then you can put a spring here, and you can talk about the energy of this object. You pull this slider down here, and the slider will go back and forth and back and forth and back and forth. Very little dissipation. It'll do this for a long time. And I was putting this up here for a couple of different reasons. One is to say that when we know how much energy is getting stored in this spring. It depends on the strength of the spring. And you can take a spring and you can hang a weight and see how much it stretches the spring. And that'll tell you what the strength of a spring is. A soft spring will stretch a lot. And so K will be a big number. No, sorry. Yeah, K will be a big number. And so, no, yeah, that's right. In other words, if K is a big number and you stretch the spring a little bit, you have to pull really hard and you put a lot of energy in. If K is a small number, it's a soft spring and you pull to put the same amount of energy and you have to pull farther. And it has this very nice parabolic shape. And so here's a plot of the energy stored in the spring against the amount the spring has been stretched away from its equilibrium zero energy position. And if you let go of the spring, the slider goes back and forth and back and forth. And what's happening there is you're seeing it start from a point like, say, here, where you've stretched the spring out and let go. The force will push the spring this way, and the energy that's stored in the spring gets converted into kinetic energy. And so this vertical distance on the diagram is seen as kinetic energy. And when it gets to the equilibrium position, the spring is completely relaxed, has no energy stored in it. It's all kinetic energy. Then it goes out here, stretches the spring, puts the energy all back in the spring, and so on. And it will go on doing this forever. And we write this down as writing the kinetic energy plus the amount of energy stored in the spring, called the potential energy. And we give it a value. And these vertical lines represent the total energy stored in the system. And so this vertical line says this energy was stored in the system when I stretched the spring out to, I think that's square root of 3 in these units, but that's it. And
Do you mean
here's
horizontal line?
this horizontal line. What did I say?
Vertical.
Well, so the kinetic energy is measured vertically from the horizontal line down to the potential energy curve. And so what you can see in this diagram is at every point of its x motion along the axis, its energy is shared between the shared between kinetic and potential. And the sum of those two is given here by this equation. And I'm showing you this equation for a reason, because I'm going to show it later. And physics allows you often, many physical systems permit you to write the energy as a sum of kinetic and some function of the spatial coordinates. Total energy we call as potential energy. So you'll see a diagram that looks like this in a little while, but it's not quite the same. Let's go back here. All right. This is all by way of getting to the point that I said is supposed to be the main message today, that quantum mechanics, in effect, well, the theory tells you what you observe in nature, which is that physical systems like a hydrogen atom do not have a smoothly varying set of energies that they can possess. A hydrogen atom, this turns out to be a complicated statement, but another way to say it is the atom, which is localized around the proton of a hydrogen atom, is, first of all, not to be thought of as a particle. It's to be thought of as some kind of a structure of waves. And the result is that the possible energy states of this atom are very distinct, very separate, and that this has some very important consequences for nature. All right. It implies discrete energies. It implies fixed geometric configurations. It implies that when we start putting atoms together, they don't go together in just any old way. They lock together in particular geometries. And now I'm going to talk a little bit about the Bohr atom. And as Peter warned you, not as Peter warned you, as Bob warned you earlier, the Bohr atom is not a fully accurate, in fairly important ways, not an accurate picture of what an atom is like. But it is historically extremely important because it is the first time that a physicist used interference to show you that this object could only have certain energy states. Interesting issue. And so here is the Bohr model is the planetary model. He thinks of, and this is happening around 1911. 14 years before we get the full quantum theory. So the picture is very simple and very seductive. The electron goes around a proton in an orbit, and you can set this up as a very simple problem in a physics course. And you can write down, we know what the potential energy is of an electron in the electric field of a proton. You can write that down. And so we can write down the equation I just showed you before, kinetic energy plus potential energy. We also know that the electric force is centripetal. And so the electron should go in an orbit. That's very much like the moon going around the Earth. And what we don't know, and what Bohr showed, was that only certain orbits are allowed. And that's what's new in this idea. And that is the idea which carries forward into quantum mechanics. Only, in fact, the word orbit gets preserved by chemists as orbital because it becomes an anathema to call it an orbit. Bob was right on my back as soon as I did. And yet they still can't give up the idea. And so orbital is a quantum mechanical version, really, in some ways. But here's the idea. Imagine a wavelength going around a proton. Can you do that? So here's the proton down here at the crossing of these two marks. And if I had a circular orbit and I imagined an electron one wavelength, so that, say, this is the peak of, so here is the peak of the wave, and it goes getting smaller, going back and back, and here is the dip valley of the wave, and here we are coming back out, and it exactly fits in this circuit. Then you see it goes on and on. If it didn't exactly fit, we could say, then you'd have the thing a little out of a line, so that one orbit where this had come to a peak, the next orbit would be a little bit less, and a little bit less. And after a while, the negative dip would come to this side. And on the average, if you constructed what those orbits would be after many orbits, it would not be an orbit. There would be zero orbit. And yet, if it's an exact wavelength, then it can go on going around and around. That's kind of what's implicit in Bohr's model. I don't know what he actually said at the time, but it is implicit. Now here, if I have two wavelengths will fit and it will keep going around and around. And 3 wavelengths will fit and it will keep going around and around, and 4 wavelengths and 5 wavelengths, and so on, but nothing in between. And that's the that's kind of, I was hoping that might amuse your intelligence and kind of give you a feeling for the creation of orbits, the creation of definite energy states. Each orbit in a Bohr model corresponds to a different energy state. I said that's not quite right. I said here, electron orbits a proton? And the answer is no, that's not. On the other hand, in 1911, it was like utter astonishing magic to have Bohr show you that the energy of the lowest energy state of a hydrogen atom would be this combination of known quantities: the mass of the electron, the charge of the electron, Planck's constant, this thing which is the permittivity of free space and shows up in electricity and magnetism. These were all known constants. And he was able, from his argument, using these somewhat questionable assumptions, he was able to show that the lowest energy would be minus 13.6 electron volts. If you put the numbers in, that's what you'll get. You'll get 13.6 electron volts. And the other orbits will be 13.6 electron volts divided by an integer squared. There's the n equal 1. That's the ground state. That's the lowest state. There's the n equal 2. Well, that's 13.6 divided by 4. That's 3.4 eV. There's n equal 3. That's 13.6 divided by 9. That's 1.4, 1.5, 1.5, and so on. And in fact, here we go. Here's what people could do. You could make a diagram, and you can put down here the lowest state called minus 13.6. I don't know if you can read that. I could make it bigger, I suppose, but I won't. And here's the other one. Here's 13.6 over 2 squared. Here's 13.6 over 3 squared, 13.6 over 4 squared. And the thing that's interesting here is that you see for the first time where photons come from and why photons come from an atom with very definite photon energies. If you had a hydrogen atom that was in its first excited state, the n equal 2 state, and it gets tired of being in that state, and it will after a while, it can only go to the lower state. There's nothing in between. Whoops. Yeah, there we go. There's nothing. Stop. There's nothing in between. And what comes out is a photon, which has an energy which is 3.39 subtracted from 13.58, which is 10.2 eV, which is an ultraviolet photon. And in fact, all the other excited states up here will come down here and make ultraviolet photons. But here's the one we all know and love, or if you're in a chemistry lab or a physics lab, this is the one you know, because the n equal 3 state dropping to the n equal 2 state emits a photon, which is the difference between 3.4 and 1.5. So call that about 1.9 MeV, EV, 1.9 EV. That's a red photon. That's this photon right over here. This is the red photon in an ordinary hydrogen spectrum. And then the next one, well, the next one has got a little more energy because he's coming from 0.85 down to 3.4. And that's this one. That's the blue one. And if you're in a laboratory, the next one is this one, and it's this one. And if you're in a laboratory, the odds are very strong that you won't even be able to see these. In fact, this you can do one of those psychological separation tests. Ask who can see it, and your aged physics professor maybe can't see this one in natural light, and your you're still, your 19-year-old physics student can see it just fine. But but on a piece of film, you can get it to record and show up with the dyes. And you can see that there's going to be a whole lot of these things. And in fact, they run getting ever closer and closer together. They run to some limit. This was all known in the 19th century. It was known and the values were known and all this known, but nobody had any idea of how it was produced. How did it come out of a hydrogen atom? And so Bohr's model showed that. And ultimately, quantum mechanics has to show that too. And quantum mechanics shows it in a way that's more complicated than we should go on with today. That is, it comes out in quantum mechanics that there are sort of clouds of probability, clouds of localization of this electron. The electron is now not a point going around a positive thing. The electron is a smear, and that is a whole new way of looking at chemistry, and it turned chemistry into physics. From 1925, 6, and 7 on, chemistry and physics were no longer at the base in any way distinguishable. A lot of practical stuff that's in chemistry that's not known by physicists, but the basic physics is there. It's all in quantum mechanics, all in these electron clouds, and they're shown here as rather complicated. And the reason they're so complicated is because I didn't tell you nearly the complications that an electron can have in its interaction with a proton. So it's this, and the forces determine the shape and the distribution of the cloud. And because of this discreteness of the energy states, atoms and molecules have a structure that we represent often, like kind of ball and stick. And it's so important that this should be so. I mean, we simply cannot imagine our lives. We cannot be here without quantum mechanics at base. This is a water molecule, and the water molecule is an amazing structure all by itself. It has an oxygen and then 2 hydrogens locate to it. It has a bond angle of 104.5 degrees. It's extremely well defined. It has this thing of the charge inside the system is overall neutral, but there's a kind of little extra negative charge gathers around the oxygen and leaving a little extra positivity to the protons. So there's a dipole moment, which is crucial to the properties of water. Water is an amazing substance. It dissolves so many things. One of the reasons it's such an amazing solvent is because it has a dipole moment. One of the reasons that it expands on freezing, which means that ice forms on the surface of bodies of water so that life can go on underneath. One of the reasons that happens is this dipole moment, this built into the structure. And and we go on, and the kind of structural building. This is a little bit more honest, and it's a depiction of a water molecule, trying to get you something a little more cloudy. But here's myoglobin, which resides in your muscles and stores oxygen for when you're running. And these are various structures go together, and it does like to bond oxygen. It's a little better than hemoglobin in bonding oxygen. So it turns out that play a very important role in storing oxygen in your muscles, which you use when you are doing athletic events, riding your bicycle fast and hard, running, jogging, all that stuff. And yet it has a structure which is representable by these ribbon diagrams. And of course, the all-time great that we hear about every time we are turning around is DNA, here shown again with kind of balls and structures, and with quite extraordinary geometric. The fact that all of these strands band together, the double helix, and the strands bonding together by these bridges. All of this is possible because quantum mechanics, well, we are inclined to say it's all possible because of quantum mechanics. And it's, of course, the other way around. Quantum mechanics is possible because this is the way nature behaves. And that is kind of the major message that I wanted to give today. But I wanted to end up with a different note, which is, I showed you this equation here. This is the potential, the kinetic energy plus the potential energy equals E. Classical equation. Now, this is Schrodinger's wave equation. And let's see, they're both telling us the same thing, but I want you to notice in the kind of parallelism between Schrodinger's equation and the classical energy equation. There's something here getting squared over 2m. There's a potential energy here and a potential energy here. And then this ends up E. This ends up E. The big difference is that here we're multiplying psi by whatever this is, and here by psi, and this by psi. In each case, we're saying that the total energy is equal to kinetic energy plus potential energy. But this is where, this is called the wave equation. Psi is the wave function. People talk about this all the time. Psi, psi turns out to be complex. I mean, this is messy. Psi star psi is the probability density that Tony and Mike are wanting me to remember. And I'm not going to go there now. Instead, I'm going to show you that this fairly, I got to say, I want to tell you what del is. Del is called del. This inverted triangle is called del or nabla, and del square, and it is a shorthand for a set of differentiations, and this del squared is the second derivative with respect to x, and the second derivative with respect to y, and the second derivative with respect to z. So this is actually quite a lot of terms. This is 3 different terms added together. But I want you to see it in this form because the folk art that I'm about to show you sees it in this form. And so Schrodinger's equation, and here is an embroidery done in 1972. Yeah, I think in the mid 70s. So it's almost 50. Yeah, it's almost 50 years old, maybe 45. But I want you to see what's here because this was done by a good friend of mine, Doris Wolf, and Doris didn't know much about quantum mechanics. I would say probably knew nothing about quantum mechanics and probably didn't care that much either. But she signs her work. If you look up here, you see, there it says, it's by Doris. And she knew that the most famous equation in physics is E equals mc squared. And so we have clouds, which here are E equals mc squared. And we have 2 clouds. Over here is E equals mc squared. And this mushroom down here is kind of an E equals mc squared, but that's the C, that's the square, but that's a little harder to take. This is, of course, that the total energy is equal to the kinetic energy plus the potential energy. And here is Schrodinger's equation redone as a kind of walking bird. Here's del squared psi on its feet. being multiplied as it ought to be by a worm, which is the minus sign, or the minus sign has become a worm. H bar squared has kind of turned into an H bar with a butterfly up here over 2m minus H bar squared over 2m del squared psi plus, and here's the potential energy function turned into a cat. You see V here, and V of, there's some kind of coordinates in there. And here, the psi has become the tail. And the two worms here are making the equal sign. And here is E, and psi, the psi is now what? I don't know, freeform peacock, maybe. Anyway, I just want you to know on this happy ending that after 100 years, the Schrodinger equation has entered the popular culture, at least on my study wall. Oh yeah, there it is. There's, I should have put that up sooner so that you could see the match better. And there it
By
is.
the way, what's the title of the slide? It's hidden behind that bar.
I can't, oh, it says, oh, yeah, I don't know why I even have a bar there, but let me see if I can move the bar out of the way. I can't, sorry. That bar has been there the whole time and nobody told me, huh? Because it didn't make a difference. All right.
Wasn't there in the very beginning, Charlie? When you flip back and forth, it popped up.
I wonder. All right, let me. Because what it says, Tony, is Schrodinger's equation by Doris Wolf. I mean, it's full credit to its creator, and so I'm embarrassed to have it go away.
Is Doris a physicist?
No, Doris is a fantastic woman. There we go. Now you can see it all. See, Doris is in sort of my age group. In fact, one of the reasons I was moved to put this up here is that I had a note on my wife's Facebook that Doris was in the hospital. And I wanted her to see that her artwork of 45 years ago was remembered, and along with her, by me. She is a wonderful, very dynamic woman who lived in upstate New York, was a stringer for various upstate New York newspapers, but far more than that, a community activist of a fairly intense and effective sort, campaigning for children, and we overlapped at Colgate University for a while. Her husband was on the chemistry department there. So she would have maybe seen Schrodinger's equation on his textbooks, but that was not her shtick at all. She was the kind of person who, raising two children, said, "You kids need pets. Let's get a couple of lambs." And so the kids got 2 lambs, and it turned out that actually they got 1 lamb. That's the story. They got 1 lamb, and he was very cute and fuzzy, but it was it was a ram, and there was a worry that somehow at some point they would want to slaughter the lamb and eat the meat, because that was the style in which the wolves lived. They lived on a little farm outside of Hamilton, New York. But the ram grew up. The lamb grew to be a grown ram. And you know what rams do is they butt you, and they knock the little kids down, and they knock the little kids down. And so on the day that the lamb was put, butting its way, in the back seat of the truck, in the back seat of their station wagon to take to the slaughterhouse, the kids stood on the porch and yelled, "Hooray!" And so anyhow, which may be a digression from what I've been telling you.
Hey, Charles, another question about the embroidery.
Yeah.
It seems that every item has some interpretation other than the sign, Schrodinger's zoo, that is obvious. But I've been wondering what the 2 posts may represent. if
Uh,
they're
oh.
supposed to have some meaning too? Are they a bunch of lines that have been just set on the vertical instead of horizontal, or what?
No, I think they're done as like posts with vines growing around them. I don't see any deeper interpretation, Tony. The picture, that's me in the middle. Until I had my cataract operation a few years ago, I always wore glasses. And I expect, I don't know if that's Doris's comment on my style as a teacher, sword and pitchfork and whip, but
You know, those look to me like spruce trees.
yeah.
Charlie, take full
There-
credit. That's an interference diagram.
Could be. That'll be, we'll know that that'll be known as the Albin interpretation.
In other words, they're the two slits.
Yeah, with hair.
The two slits with their interference.
Oh,
I don't think she knew that much physics.
no, and you see, I'm having trouble making that. I would think of those more as spectral diagrams, and those are just line spectra.
Okay.
Except they're all green, which is not good.
Well, on the old oscilloscopes, they probably would be.
I like your style, always. All right, let's see. So there's 5 chat remarks in here. Are these all questions?
So that's, Charlie, while you're looking at that, that's the beauty of art. You can take away from it anything you want.
Right.
I liked her signature, Doris. I would never be able to guess it, but yeah, you can read it.
Well, that's the way it is with art critics. You know, they take you to a piece of art and they talk about it, and afterwards you see all kinds of things you never saw before.
Bob, Bob Primack, was it you who last week or the week before said about electrons rotating and orbiting? It's like the moon orbiting around the Earth and rotating on its axis, except that it doesn't rotate around the nucleus, and it doesn't orbit around the nucleus, and it doesn't rotate on its axis.
Electrons don't actually spin.
Well, we don't know what they do.
They have a property called spin, and it is an angular momentum property, but they aren't actually spinning. They may not even be points. They may be standing waves in an atom.
Well,
Yeah, Charles,
no-
probably you can comment on the analogy between the particle you showed us earlier made out of 30 harmonics, and then the Dirac's delta function, which essentially is the superposition of all frequencies with equal amplitude.
and what would you like me to comment on?
Well, I mean, like the function seems to be like a particle being very localized and spiky.
I mean, we use the Dirac delta function anytime we want to represent a particle, but we know it isn't true in the sense that here's another. Let's repose this question in terms of the electron. Nobody has ever seen any evidence of internal structure of an electron. Nobody has ever seen evidence of finite size of an electron. Now, we don't know that, because here's an interesting point. Go back to this business about localization and energy. Another way to say the same thing is, if you want to look at something small, you better look at it with a wavelength which is of the size of the object you want to look at, or smaller if you want to see structure. So how do you make small wavelengths? You build humongous big accelerators, and you give a huge amount of very well sharply defined momentum to something. Electrons, maybe. Protons, maybe. And you send those crashing into an object to see if you will see any structure. Nobody has ever seen, at the highest possible energies, any evidence of structure of an electron. We still refer to it as a point particle.
Yeah,
calling something a
lepton,
point particle is very uncomfortable because that gets you into singularities when you talk about the mass of the object. I mean, an electron certainly has mass, and if that mass is concentrated in zero volume, then you've got an infinity going there, and nobody knows how to deal with that really.
yeah, electrons are considered fundamental particles along with photons, but the hadrons, the heavier particles, are believed to have further structure.
Yeah, well, all kinds of things. You know, now we're wondering about, do quarks have further structure, or are they fundamental particles? But the business of trying to find a radius of an electron, there is something called the classical radius of the electron, but there has never been any physical manifestation of a radius of an electron.
Adam, did you want to comment on the force and energy remarks you made in the chat?
Oh, it was just when the discussion was being had about the energy, the depth of the energy well, and because the energy well was deeper than 4 electron volts, wouldn't that pull the electron in? I was just trying to offer a different way to clear that up, which was the depth of the well is a separate thing from the force pulling the electron in, even in a classical sense. It's the gradient of the energy that is the force, not the depth of the well itself.
Yeah.
So it was a while ago now.
Anyway, no, I mean, Adam is quite right. I was trying to avoid those topics, and see, I mean, and I think I'll continue to try to avoid them. That's
Good. And Mike had a comment he sent to me directly, but I think it was supposed to be to the group. And he's talking about wavelengths and orbits, first advanced by de Broglie.
so. What did Mike? You there?
He is, yeah.
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 Really?
At least the way I learned it, you know the history better. I thought that the wavelength argument was advanced later on by de Broglie.
Yeah, I said that of it. I mean, in just passing, I said the Bohr didn't do it this way.
Yeah.
I mean, yeah, Bohr had done the Bohr model, and he had, as we would say today, he had quantized angular momentum and didn't know that. And quantizing angular momentum is the same thing as requiring the wavelengths to become exact orbits, each orbit to be exact integer number of wavelengths. And he didn't know that either. And it didn't make any difference. He did a lot of things which made the world uneasy, made physicists reel in horror. But in fact, when he got that 13.6 electron volts so precisely from all those constants that had just been lying around, everybody had to shut up and say something big is going on here, and you know, straighten it out later. I forget. Einstein had once made a remark about Bohr's thought being of a very high order of musicality. I think something like that, and he was, Bohr was famously inarticulate. I remember he was giving a lecture somewhere, and 2 physicists were arguing about whether he was lecturing in English or in German, or maybe it was in Danish. But he had a thick accent, and he had to hunt for a word. He always had to dictate his papers. Even his first science papers were dictated to his mother, and then he always had to have a confrère to whom he dictated, because he pressed always for very precise logical arguments, and strained for them, and produced extremely interesting, well thought out results. But it was, Hans Bethe, on the other hand, was said to always dictate full papers, 1 draft only, no revisions. So you got kind of polar opposites there. But okay. Again, I digress.
Dick, go ahead.
Yeah, I wonder if I can make a couple of humble comments here. I thought Charlie's talk was outstanding.
I don't think, Dick, you make humble comments, but go ahead, make comments.
Okay, the first one is, this always intrigued me that Planck's constant, the units for it are in angular momentum. And that may be why we have this confusion about orbits and in the hydrogen atom. And talking about orbits all the time, because you have an angular momentum aspect of in quantum mechanics for energy that came out of Planck's constant. Second comment is going back to one of the first things that you said about why we're not emphasizing quantum mechanics earlier in the educational process. And I thought about that too, and I agree with you. And I came up, maybe a month ago, with what I call a modest proposal, giving some credence to Jonathan Swift, who
I was going to say, we eat the babies, right?
Oh, you know the modest proposal. Yes, that's right. It's a short essay, but outstanding. Anyway, maybe this will fit in the same scheme. I don't know. But my thought is that we start out teaching people about waves, and that when we talk to even kids, we talk about waves rather than talking about particles or masses going up hills or gravity or things like that. We talk about waves, and we get people thinking about waves, and then get to the wave equation, or at least get to waves and talk about superposition. I mean, we see waves all the time, just like we see masses. We see superposition, we see positive and negative effects on waves. And then from there, I'm thinking, well, perhaps we can get to the Schrodinger wave equation then, which then introduces some math into the quantum mechanics, because the Heisenberg matrix theory is a little bit, at least it used to be, not taught too soon in math. You could teach that early too, I suppose. It's not that difficult a mathematical concept. So we could get to quantum mechanics, I think, faster and easier if we just started people off thinking in terms of waves rather than particles. Because you can always come to the particles, I think, as you pointed out, you can always get to the particles, the mass to the energy from quantum mechanical calculations. You eventually get there with the wave equation. So you don't have to do Newtonian mechanics to get to that point.
Yeah, I'd like to comment about how easy matrix math is. It's not for me.
Well, it wasn't for the physicists in the day. There was the initial investment was to a remarkable extent in the wave equation and finding solutions to it.
Yeah.
Partly because they knew how to find solutions to wave equations. They had done that in the 19th century. But you had to, who was it?
But I think, yeah, the wave equation that comes out because we know we can do calculus, we can do differential calculus. That's why we can do wave equation relatively soon, because we get calculus soon. But if you got matrices and vectors and matrices early on in your math, to me, that's a relatively simple concept, just a bunch of numbers inside a box. And you just learn the mathematics of multiplying, adding, and so forth of it. And you can use it. So
And it's that math which to myself and to a lot of children is not easy to grasp. Well, how you manipulate these matrices.
Yeah. So I would say that this is an issue I've been worried about for a long time. Actually, I've done something about. I've written a textbook for introductory physics, which gets a fair amount of quantum mechanics in the first semester, but it doesn't do it either by the wave or matrices. It does it really using the Feynman probability amplitudes approach. Because you can avoid both those mathematics. I think the Schroedinger wave equation is a very tough row to hoe, except for a few simple cases. Yeah. And you're generating orthogonal polynomials of all kinds of weird sorts. It's a rough piece of mathematics, I always thought.
Yeah, I agree.
Yeah. Whereas to multiply matrices together, isn't that hard, but it doesn't get you where you want to go. You got to do matrix eigenvalue problems, and I don't want to go there either. Not in beginning physics. I'm with Bob on that.
Well,
And,
the reason I say it is because I want to get the concept of waves out there a lot more. We don't really think about waves until far into our physics curriculum, I think, and I think we should begin. That's what I want to stress, is that we
certainly
should
back
talk about waves
in
early.
back in the 60s, there was a lot of experimentation. We got the Feynman lectures, and we got Purcell,
Right.
we got the Berkeley series, but there were also a couple of people. I can't remember his name right now, but anyway, he wrote a book which basically starts physics with optics. A lot of people say start with optics because first of all, there are a lot of simple stuff you can do. Mathematics isn't bad, but then you can get to waves and,
Right.
and do it there. There are a lot of ways to skin a cat.
There's
Can I
another
just
way.
add something?
Yeah, go ahead, Cindy.
After your first lecture in quantum physics, I knew nothing about it. There was a lot of content, but it certainly piqued my interest. And I wanted to start from the beginning. So I just went to Googled YouTubes for kids on quantum physics. And there were a couple of them who were very good and explained in almost a cartoon fashion waves. So there is stuff out there. And if you remember one talk we had where they explained a complicated topic in 5 different levels. I don't know if any of you are on that, but they started with the basic, young kids could get it. And then just the next talk went up to teenage level and up and up and up in complexity. So
yeah, we have several videos of 5 different levels that we're considering for future sessions.
Yes, and those were excellent. And when you were talking in the beginning, Charlie, I thought, oh, well, 2025, perfect. That's a perfect time to have a children's book on quantum physics and start it in on the different levels.
Cindy, just to pile on what you're saying, 2 things. There's an organization called Khan Academy, which is fantastic, that if you're looking for a simple explanation or even sometimes a complex explanation, they have videos done by professionals in a professional way that take these subjects at the school level and explain them very well. You can find whatever level you're looking for there generally pretty easily. And the other point I wanted to make, Charlie, is that you talk about the wave stuff and matrices. Matrices became easy when computers came around. I mean, when you still had hair on your head, we both did, and we were both very young. Did you really want to do matrix multiplication?
I never had any trouble with it. Once I learned this, what is it? Someone told me I need a big screen. I can't do it. Anyway, there was this thing where you go with your fingers.
Yeah.
And you now know how to do matrix multiplication.
But admittedly, it's tedious.
Well, I stick with 2x2s. I mean, no.
But you don't even want to. You don't want to think in terms of.
It's a little difficult.
Yeah, you don't want to think in terms of matrices because what the quantum mechanical description later came into was vectors, and and the matrices are composed of vectors, so you can visualize vectors and orthogonality and stuff like that, and so I mean, the way it's taught, that comes much later. But getting bogged down in matrices, I think, is a problem. But
yeah. Well, I mean, I think if you're talking about doing something early, which is what I am a big advocate of, getting I was shocked, simply shocked to find that kids taking the required introductory physics course at MIT did not run into Planck's constant. And
Here.
And I think, what? I mean, there are ways that's maybe a little extreme, and and they are trying to fix it a little bit. But I mean, they don't even run into that E equals h nu, the frequency of a photon. That's terrible.
That's because Planck didn't go to MIT.
Oh, but, but
Uh.
the introductory physics course isn't addressing just future physics majors. A lot of the people who are taking that course will never get involved in quantum mechanics at all.
I think you're wrong. I mean, I think, in fact, anybody who's doing material science, anybody who wants to understand what's going on in the newspaper, anybody who wants to understand why these guys are once again asking for more money to increase their research, needs to have run into Planck's constant. You do not understand, and as I was saying earlier, you do not understand the definition of the mass of the kilogram without knowing what Planck's constant is.
And also,
Which means that
trust me,
everybody, nobody in the world anymore understands the definition of the kilogram. But
trust me that what's going on in biology today is getting more and more toward quantum theory.
Sure.
Okay, so it's getting there.
And who was it said? Was it Steve who said at the beginning? He quoting someone saying, "In physics, progress is one funeral at a time."
I think that's Max Planck's quote.
Who
You're
said that?
talking about quantum mechanics. Let me show you this. I don't know if you can see that or not on Scientific American.
Yeah, you can. Quantum navigation. Yeah.
Yeah, quantum navigation, and it actually explains how the Robins, use the quantum pairs in their eyeballs and the brain. It's a good article.
Well, I think you should be wary anytime you see the word quantum. It may be for an underarm deodorant, but and it'll be claiming wonderful properties. But
No, they actually said what you were saying is that the nature has a lot of quantum effects in its, and we're just understanding it now.
yeah, well, I think we're quite a ways.
Yeah.
Well, the entire way that we get food, where plants make food by photosynthesis, there's a lot of quantum stuff going on there.
Yep.
Yeah.
It's absorbing photons for one thing.
Exactly.
And it's got very high energy states in its molecules.
Yeah.
You think the plant knows that?
They don't need to. Just do it.
They don't
We don't need
care.
to know how we see in order to look at something.
Okay.
You don't need to be dead to write an obituary, right?
Right.
In a little
And if
bit
you
of-
don't go to your friends' funerals, they won't come to yours.
Yogi Berra said that.
Yeah, I know.
But
it.
nobody can tell us what heaven is like until they've been there.
listening to the conversation.
It looks to me, it sounds to me like we're done.
And, I was going to bring that point, but is there a danger of trying to take what we call quantum theory today and try to use it to explain everything,
Of
when in
course.
fact it may or may not be true?
Well, we know it's not true. I don't know. There's no problem there. There is no connection between quantum theory and gravity.
Right. That's the
And
big problem.
That can't be the whole business of what is it? Dark matter and dark energy. Those two
Right.
things. Those are two great big fat ways of saying we don't know what's going on.
Right.
And the kind of desperate search to answer the question of what's going on by finding particles, that could just be a completely blind alley. I mean, it might be, we don't really, I do always keep in the back of my mind Abbott's Flatland, where, it's a lovely little story of what does the world look like to these people, and when three-dimensional objects cross their boundaries. We could be living like that. There's nobody says that we're stuck with 3 dimensions or 4 dimensions or 5. It could be some weird stuff that we just plain don't understand. And then anyway, it's nice to live with some mystery.
I have one weird thing that you might like, as physicists. If you remember on Channel 2, PBS, they had the mold, that one cell mold that, just goes, it finds food, it does this, it does that, but it has no brain.
That was
Remember that?
Nova. Yeah,
Yeah,
that's
I
slime
know,
mold.
yeah.
Slime
Yeah.
mold at work. Oh,
Okay. Now let me throw this out. Think about the networks they've shown about dark matter. It looks almost like the same structure as the mold.
Oh, good point. So they
You
should
know,
use, maybe they can
because-
use slime mold to calculate the internet, but it depends on
Well,
what
it's-
snowflakes are.
Yeah. Well, especially when there's certain areas where on the network a lot of stars are formed, and then in other places stars are not formed. Based on this dark matter network. It's really weird.
No,
That's
it's
why I
actually-
brought it up.
Yeah.
David, it's actually redlining, so don't worry about it.
I don't worry about it.
Oh, on higher dimensions, doesn't string theory depend on higher dimensions?
Yeah, but nobody really knows what string theory is good for.
Right.
If anything. I mean, actually it's turning out to have some nice applications in solid state physics, but it is not answering. It has a kind of general structure that would permit combining quantum and gravity, and that makes everybody look at it hungrily. But there's no guarantee that that's the answer either. And
The problem is, how do you experimentally confirm string theory?
That's right. When you can travel into another dimension. Come on.
Well, maybe somebody already has.
You have to go through a wormhole.
That explains how I got here, does it? Okay. All right, guys.
I think we've exhausted this pretty well. I'm going to call the meeting adjourned unless somebody has something important to say.
All right. Well, I don't know if there's going to be a part 3. The original idea was to have 3 parts because we're supposed to get to entanglement in qubits, but maybe I'll quit while I'm winning.
I think you're doing fine, Charlie, and it was really great. Let me go to the Wayback Machine in my head. Jerry, are you doing something next week?
Yeah, it's something that actually the audience will understand.
There we go.
Thanks, Jerry.
Ooh.
Yeah.
Brutal.
Jerry wonders why nobody likes him.
Here comes the Will Smith hand slap.
I used to have a dog that I had a dog who liked me.
But he died.
We had him put to sleep.
Notice the past tense. He had a dog that liked him.
Right. And then we put him to sleep.
There we go. Liking you too much. All right, everybody.
All right.
It's been a great meeting. Thanks a lot, Charlie. Really appreciate the work and effort.
It was a good time. Great time. Great time.
All right. Good questions, guys. Thank you. You're a good audience.